Hello guys, this is Prime Concept. So we want to quickly get into our revision class continuation. Remember we started our revision in the last live session we have on Sunday. So today we'll be looking at how to fasten our studies. And our last class on Sunday, we considered a whole lot of things from electrostatics to Gauss law. So this time around, we're going to take a different approach that will help us be very fast with it. So we are going to approach it by solving of problems on this topic. So I'll pick the first topic for today, explain just a few concepts, to look at problems. So, but before we start fully, I want you to begin to share the video, invite your friends, tell them we have started. Tell them we have started. How many persons do we have now?
8.
8. Please share and tell your friends who have started. So we need more persons on the live so that we can push. I don't want them to come late and then we have gone too far. Please share, like the video, share with your friends, invite them, tell them Prime Concept is live. Invite them. How many do we have now?
7.
7, okay. Invite them, invite your friends. So it's a very important thing we want to look at today. We'll be looking at a whole lot, but we'll be doing this within a short time. So we have a few topics left, and the topics we have includes capacitor. I think that is where we should pick up from capacitors down to Maxwell's equations. So let me just try to do a quick summary on capacitors, then we'll take problems. Capacitors. And first, we know that capacitors are devices that store electrical energy, or you can say capacitors are devices that store charge in an electric field. Remember, the counterpart for a capacitor, remember, since we are revising, for example, I'll be pointing a whole lot of things at the same time. The counterpart for a capacitor is an inductor. So what a capacitor does in an electric field is actually what an inductor does in a magnetic field. So if we say a capacitor is a device that stores energy in an electric field, then we can say an inductor, on the other hand, is a device that stores energy in a magnetic field. You should take note of that. Now, that is what a capacitor is. We have different types of capacitor, but for your level, we are considering the parallel plate capacitor. Parallel plate capacitor. A parallel plate capacitor is actually a capacitor that is built by two parallel plates. Say I have something like this. This is a plate, this is a plate, this is another plate. So if I bring these two things together, metallic plates, conductors, if I bring them close to each other and connect each to a battery, it becomes a capacitor. So we have the parallel plate capacitor, right? Then we have what we know as capacitance of a capacitor. Capacitance. Since a capacitor stores charge, it means that different capacitors should have different capacities. This one may be able to store 2 coulomb of charge. This one may be able to store 5 coulombs of charge. So the capacity of a capacitor is what we call capacitance, and it is denoted by capital C. Capacitance of a capacitor. So what is capacitance of a capacitor? The capacitance of a capacitor is the ability, is a measure of the ability of a capacitor to store charge or store energy. So it measures the extent to which a capacitor can store charge. That is what we call capacitance of a capacitor. And the capacitance of a parallel plate capacitor is C, which is equal to epsilon naught for free space times A over D. So this is the relationship you need to know for capacitance of a parallel plate capacitor, right? Yes. And secondly, you should know that capacitance is measured in farad, the unit. Like I told you, exam would ask a lot of questions around units. So take note of it. The formula for capacitance of a capacitor is C equals this times this divided by this, and the unit is farad. Now, what else do you need to know? Exam question asked, there's a question I saw that said To achieve very large capacitance, what variables must be considered in designing the capacitor? To achieve very large capacitance, what variables must be considered in designing the capacitor? So this question is very simple, which comes from what I've given you now. So you want to achieve a large capacitance. The variables to consider is one, the cross section. The cross section, which is what you know as area, the cross-sectional area, is one variable to be considered. Now, how does the cross-sectional area determine the largeness of a capacitance? You can see the relationship. Capacitance is directly related to cross-sectional area. So it means that if you have big area, you have a large capacitance. So that is one of the factors. Then another variable is distance. Distance between the plates, which is denoted by D. So you can see that capacitance and distance are inversely related, which simply means that if you need a large capacitance, you need to decrease the separation between the plates. So distance is the next variable you should consider. So you have to use a small distance so that your capacitance should be what? Should be high. Then the third parameter you should consider, who can tell me the third parameter we should consider? Very quickly, the third parameter is the dielectric material. Now, like I said, that parallel plate capacitors are built by two parallel plates like this. Now, most capacitors are not, practical capacitors are not built this way. They always put an insulating material between the plates so that these two plates don't touch each other. And that material they put in between is what we know as a dielectric material, right? So it means these are the three factors that can influence the capacitance of the capacitor. So the higher the dielectric value, the higher the capacitance. That is what this epsilon permittivity is talking about. So these are three things you should know about the capacitance of a capacitor. Now, I've given one relationship for capacitance. Another relationship you need to know when you're dealing with capacitors is the most important, which is Q equals CV. This is the origin, actually. Q equals CV. So charge is related to capacitance from this formula. So these are formulas we should know for capacitance of the capacitor. And the next thing you want to learn under capacitors is arrangement of capacitors. Now, you can arrange capacitors. Meanwhile, before I continue, how many persons are present now?
22.
So we have 22. So it means we should move on. Now, before we look at arrangement of capacitors, let's quickly solve one problem under this. I have a question. So should I read it out or write? Drop your suggestion quickly. You want me to read it out or write? Because I want to finish this class in 1 hour and I want to cover at least 4 topics. So should I read it out? Tell me fast so that I'll know which approach to continue with. All right, what are they saying?
Right.
Right. Wow. Okay. I will be writing and reading at the same time. So I have this very interesting question, which says a 1000 microfarad capacitor. A 1000 microfarad capacitor is charged. Okay. A 1000 farad capacitor is, where is the question now? Okay. Initially uncharged. Sorry. Initially uncharged is charged by a steady current. a steady current of 50 ampere. How long will it take for the PD, that is potential difference, across the capacitor to reach 2.5 volts? I'll give you 30 seconds to attempt this question. It's on the board, so I believe you can see it now. 30 seconds. Remember your exam. For some of you, those in engineering, your exam is tomorrow in UNN, while for some other persons, their own is, I think, next week. So at this point, you have to be very fast in producing answers. So 15 seconds to go. Any answer yet?
Not yet.
Okay. So who are those present? Let me give shout outs to them.
We have Innocent.
Innocent, thank you for participating.
Nnadi Lotanna.
Lotanna, thank you.
Pascal. Chike Chisom. Ike Elizabeth.
The first lady, all right?
Rodo Okuma.
Chukwuemeka. Nkemjika. Sport expertise. Okay.
Odo Victor.
Chinonso. Lillian. All right, so that is good. So I hope to see you guys at the end of the video. I'll be giving a shout out to those that will stay till the end, and do well to invite your friends for this. Now let's solve together. Any answer yet? All right, let's solve together. The question says a 1000 microfarad. And first, you should know that the capacitance of the capacitor C is given to us as 1000. Now remember, micro simply means times 10 to the power minus 6. Then I will include my farad. So it means this. Remember, 1000 is same as 10 to the power 3. 1000 is same as 10 to the power 3. So I can write this as 10 to the power 3 for 1000 times 10 to the power minus 6. So that this can actually simplify. 3 minus 6 is actually minus 3. So this same thing as 10 to the power minus 3 farad. So this is my capacitance. I've not solved yet. A 1000 microfarad capacitor, initially uncharged, is charged by a steady current of this. So they gave us current that charged that capacitor as 50 ampere. Now, how long? How long is talking about what? Time. So we're trying to find how long will it take for the PD across the capacitor to increase to 2.5. So they gave us the voltage, 2.5 volts. So we're looking for time. Very quickly, there are two important formulas you should know. One of them is from capacitors. The other one is from direct current. So we know that charge on a capacitor Q is CV. We also know that charge is equal to I what? IT. So it means we can equate these two quantities and find time. So that I can say that IT equals CV, and then T becomes CV over I. So I believe at this point, everybody can produce the answer. So I'm rubbing the question. I would have space. So my time T is going to be C, which is 10 to the power minus 3. The voltage is 2.5 divided by my current, and my current is 50. So punch for me.
5 times 10 raised to the power minus 5.
Minus 5.
Yes.
Seconds. Yeah. So you see that the capacitor charged within a very short time. Any answer?
Chukwuemeka
got the correct answer.
Yes.
Thank you.
Charles got it.
Charles.
Yes.
Thank you.
Nkemjika got it.
Nkemjika, thank you. So I'm happy that you're following with what we're doing. So quickly, what I needed to do is to screenshot so that I can move on without wasting time. You screenshot the solution and we move on, all right? To save our time. So quickly, let's move to arrangement of capacitors. We've talked about a capacitor. We've talked about capacitance of a capacitor. We've talked about the factors that affect the capacitance of the capacitor, which includes what? The cross-sectional area, the distance of separation between the plates, and the dielectric material between the plates. These are factors that influence that influence capacitance of a capacitor. Now, next, we want to talk about arrangement of capacitor. Capacitors can be arranged in two ways. One of them is what you know as parallel arrangement. Now, one of the things you should know so that it doesn't confuse you is that the arrangement of capacitors is opposite to that of resistors. So pay attention so you don't mix them. So number one is parallel arrangement of capacitors. So how do you arrange capacitors in parallel? Whenever you have capacitors like this, the diagram for resistors and capacitor is the same, but the formula is what differentiates them. The diagram for parallel is the same. So say this is a battery. Now I have two capacitors. This is C1, this is C2. So these two capacitors are actually connected in parallel. You can see it in line. While this is my battery, my voltage. So this is a parallel arrangement of capacitors. Now when you have capacitors arranged in parallel, how do you get their equivalent? When capacitors are in parallel, the equivalent capacitance is direct addition. Is direct what? Addition. So it's going to be C1 plus C2 and so on. Look at the arrangement. The equivalent is direct. It's not 1 over. So don't mix it. Assuming you were dealing with resistors like this, it will be 1 over. But since we are dealing with capacitors, they are in parallel, you add them up, not the inverse. Now, what are the points you need to know for parallel arrangement of capacitors? Number one point I want you to know for parallel arrangement is that when capacitors are in parallel, the voltage of each capacitor is the same. So it means that the voltage in this place is V, which is actually this total voltage. The voltage in this place is also V. The voltage of each one is the same. But what is different for them? Number two, their charges are different. So the charge in this place is Q2. The charge in this place is Q1. So what are the 2 points to note? When capacitors are in parallel, voltage is the same. Charge is what? Different. So these are the take-homes that you need to have. Now, then number two arrangement for capacitors, before we take problem again. Number two is your series arrangement. Series. So what is the diagram for series arrangement? So this is how capacitors are arranged in series. Before I continue, remember that the symbol for capacitor is two equal lines. But this one is longer than the other. So this is battery. While this one that are equal is capacitance. So this is C1, right? And then this is C2, this is the voltage. You can see that these two resistor capacitors are connected in series, right? While in this case, they are connected in parallel. So now we're looking at series. Now, when you have capacitors in series, what do? The equivalent is going to be like this. 1 over C equivalent equals 1 over C1 plus 1 over what? C2. So this is how you can solve for capacitors in series. Take note, it is the inverse when it is in series and the direct addition when it is in what? Parallel. So take note. Now, what are the two important points you should note here also? For series arrangement, voltage is different. Voltage across each is different. So it means in this place, I have V1, which is not the same as this. In this place, I have V2, which is not the same as this, but the charge in each capacitor is what? The same. So in this place, I have Q and I have Q. I'm not saying Q1 or Q2 because they are the same, right? So I believe this is very clear to you. Now let's take a very simple problem from our exam pattern. So let's see. Now we have the question here. The question says, the combined capacitance, let me write it. The combined capacitance of two equal capacitors connected in series is equal to. So that's the question. The combined capacitance of two equal capacitors. So take note of the word equal capacitors connected in series will be equal to what? So I'm waiting for your answer. Quickly. I have options. If you want, I can mention the options for you. So first option says it will be 1/2 the capacitance of one capacitor. Second option says it will be twice the capacitance of one capacitor. Third option says it will be 4 times the capacitance of one capacitor. Then fourth option says it will be 1/4 the capacitance of one capacitor.
Chukwuemeka said that it is half.
Okay, Chukwuemeka, that it is half, right?
Yes.
Okay, who else?
Judith.
Judith.
Precious.
The same thing?
Yes.
Judith Precious says is what?
Half of
Half.
the capacitor.
Okay, any other answer?
King Justice said A. The answer is A.
Okay, A. All right, let's verify. Let's solve so that we can move on. Now, see the question. They said two combined capacitance of two equal capacitors. The capacitors are equal. That is to say that C1 is equal to C, then C2 is also equal to C, since they are connected in series. So if they are connected in series, you know how to find the equivalent. So they now said what will the combined capacitance be if they are connected in series? Now, when you connect capacitors in series, to get the equivalent, you say 1 over C equivalent, which is equal to 1 over C1, and C1 is C, plus 1 over C2, and C2 is C. So I have 1 over C equivalent equals this, which is going to be 1 plus 1, which is 2 over C, because the LCM is C.
Yes.
So this is what I have, right? Now, well, this is not my answer. So I need to find C equivalent. This is 1 over C equivalent, which is 2 over C. It means that only C equivalent will be C over what? 2. So you can quickly see that their combined capacitance will be half of each of them. Remember, each of them is C. So the equivalent is just each of them divided by what? 2. So it will be each of them, right? Yeah, so I believe it is clear. So Chukwuemeka also got it.
So many of them.
So many of them got it, right?
Yes.
All right, so thank God you're getting it. Now let's take another problem quickly. Remember, we have to be fast. We're soon going to be done with capacitors. We get to direct current. So I have this diagram. Is 1.8 microfarad. This is 1.5 microfarad, and this is connected to a 12 volt source. 12 volts. And the question says, what is the charge on the 1.5 microfarad capacitor? What is the charge on the 1.5 microfarad capacitor? That is the question there. What is the charge? So I'm giving you 30 seconds to solve this. Meanwhile, please make sure you have liked this video. If you are part of it, make sure you like it. That is your way of supporting it. So like and share to your friend personally. Tell them that prime concept is life for your revision against your exam. To invite somebody, like, comment, always drop your answer, participate in the video. So I'm waiting for your answer. Any answer yet?
Not yet.
Okay. So what is the charge on the 1.5? Chukwuemeka?
39.6.
Huh?
39.6 microcoulomb.
39.6 microcoulomb. All right, Chukwuemeka, I love that.
Ozzy said 1.80.
1.80.
Yes, times 10 raised to the power minus 5.
Times 10 to the power minus 5 coulomb.
Yes, King Justice agree with Chukwuemeka.
Okay.
Nkemjika agree with Ozil.
Okay, they are sharing it.
Then Eziwere Miracle said 18 microcoulomb.
18 micro, okay, similar to this.
Yeah.
Okay. Okay, now let's do it together and verify our claim. Now we have this circuit diagram. Of course, you know that these capacitors are arranged in parallel. You can see it, they are in parallel, right? Yes. Now the question says, what is the charge on the 1.5 microfarad capacitor? First, you need to ask yourself, when you have capacitors in parallel, what is constant for them? When you have them in parallel, what is constant for them? Voltage here is 12 volts. The voltage here is also 12 volts. That is the first thing you should know. And their charge is different. The charge in this place, I'll call it Q2. The charge in this place, I'll call it Q1. So if you know this, you have solved it. So we know that for capacitors, Q is equal to what? CV. Now, since I'm interested in getting the charge for the 1.5, I will just deal with what I have here. I don't know the charge, I know the voltage, I know the capacitance, so I can solve. So quickly, my charge Q1 is going to be the capacitance, which is 1.5. Now take note of the fact that you need to include the microfarad. So times 10 to the power minus 6, which is micro, then times our voltage, which is 12. So if I solve this, what will it give me quickly?
1.8 times 10 to the power minus 5.
1.8 times 10 to the power minus 5 coulomb. So I think these people got it, right?
Yes,
yes. Who is that? Nkenjika.
Ozil.
Ozil. Yeah. So this, of course, you can still put it in micro, right?
Yeah.
If you move forward, this will just be 18 micro coulomb. You can still put it this way.
Nnamdi did that.
Okay. Nnamdi Charles got it also.
Yeah, the same 18 microfarad.
Okay, so this is good. So quickly screenshot it so that we can move on and save our time. We want to take another problem before we now look at energy stored. We want to take another problem. So screenshot. Can I rub now? Can I rub? Respond quickly. Can I rub? Yes, I should rub. No, I should wait quickly. Any response?
No.
No response. Be fast. So we can save time.
Yeah, you can rub.
Thank you. Now, I have this circuit that a lot of students have showed me, even on our group. A lot of people, but it's a very simple question. So do it very fast. So we have this. This is 5 microfarad. This is 2 microfarad. This 45 microfarad, which is too large. Maybe it's supposed to be small, but let's work with it. This is 2 microfarad. This is 6 microfarad. This is 3 microfarad. I think this is the diagram. The question says find C equivalent. Find C equivalent. That is the question. So I think I'll be solving it straight away so that we can save time. Find the equivalent capacitance of this circuit, right? Now, before I start solving, I want to quickly inform you that if you have only 2 capacitors that are in series, you want to get the equivalent. Say you have C1 and you have C2, and both of them are in series. Take note of what I've said. Then you don't have to go a long way. You want to find the equivalent, you just do the equivalent is their product over their sum. What do I mean? You just say C1 times C2 over C1 plus C2. That is how you get it. So this is a very fast way of solving problem in exam. So if you have only 2 in series, you do their product over their sum. So take note of this. You can screenshot it as well. Let me rub it so that we can solve this problem. Now, let's solve. When you're solving something like this, when they put something like this, it simply means this is your terminal. This is where voltage is to be connected. So you don't analyze circuit from this side. You analyze from the other end and be folding forward. So I'll do it gradually. Now, first, you want to notice that these two capacitors are in series. You can see them straight. It means that this and these are series. So how do I find the equivalent for these two? I would call it C equivalent 1. That is my first equivalent. Since both of them are in series, I would use the idea of what? Product over sum. So what is it going to be? It's going to be 2 times 6. Then you say 2 plus 6. Now, please take note. When you're trying to find equivalent, you don't have to convert this micro. Leave it the way it is. Just be using the values. At the end, your answer is going to be in micro. So don't say 2 times 10 to the power minus 6 times 6 times 10 to the power minus. Don't do that. You complicate your problem. So just use the values the way they are. So I have from here 2 times 6 is 12 divided by 8. So punch for me is 12 divided by 8. I think this should be 1.5.
Yes.
1.5 microfarad. Now, I'm going to redraw the diagram. So I expect that you should have screenshot this. Because as I'm finding the equivalent, I'll be cleaning. So do well to screenshot the diagram so you know what we're solving, right?
Some have even finished.
Some have finished solving. So tell me your answers, those that are finished, so that we'll wait for you.
Miracle said 4 152 microfarad.
15 microfarad. And Miracle, all right?
Chima said 5.89.
5.89 microfarad. Chima.
Yes.
Who else?
Nkemjika 4.15.
4. Same thing, maybe 4.15. Who else?
And Okoma said 4.25.
4.25 Okoma.
Yeah.
Okay, now let's continue.
Chukwuemeka said 17/4.
Chukwuemeka 17/4. Now let's do it. So please, I believe you have the diagram now. I'll be rubbing. Now I've gotten the equivalent of these two, which is now 1.5. So I'll rub. So it means this is only one capacitor here now, which has a value of 1.5. Now you notice quickly that this and this are in what? Parallel. Since both of them are in parallel, I will add up. So my equivalent 2 for these two is going to be direct addition, which is 3 plus 1.5, which would give me 4.5 microfarad. So quickly again, I would redraw, since I would have to remove this, and I have only one capacitor, which is just this with a value of 4.5 microfarad. You can see the circuit is simple. Now, next thing, you'll see that this are in series. Don't touch this yet. This are in series. So I can resolve this as 1. So I'll call it C equivalent 3. Now, since they are in series, how do you get the equivalent? You do inverse for series. So I'll say 1 over C equivalent 3 equals 1 over the first one is 5, plus 1 over the next is 4.5, plus 1 over the other one is 45. So I have this equal to, what is my LCM going to be? I think I can go with 45. So 45. So 5 in 45 is 9.
Yes.
9 times 1 is 9. Plus 4.5 in 45.
10.
10. So I have 10 plus 1, right? So this is 20. So 20 over 45. So it means that my C equivalent 3 is going to be 45 over 20. Give me the decimal.
2.25.
2.25 microfarad. But am I done? No. So it means that this 3 would now be 1. So I can now do like this. This 3 becomes 1, which has a value of 2.25. Now you can see that this and this finally are in what? Parallel. So my final equivalent is going to be the direct addition, which is 2 plus 2.25. And my answer is 4.25. So who got it? Okay, only one person got it. Who is that?
Okoma.
Okoma, congratulations, Okoma.
Chukwuemeka got it.
Chukwuemeka got it also. Congratulations, I'm happy.
It's all good.
Okay, so quickly screenshot so that we can move on. Screenshot. The next thing I want to talk about is energy stored. Then we'll talk about energy stored. I think we'll draw it to and talk about dielectric. We are done. We'll move to the next part. So screenshot. Can I move on? drop your answer. Say yes if you want me to move on. I don't want to be fast. Or you say wait if you want me to wait. Any response?
Yes, yes, yes.
I should move on.
Yes.
Okay. So we want to talk about energy. Energy stored by a capacitor is the work done. That is by definition now. Energy stored is the work done in charging or discharging anyone, or discharging a capacitor from zero potential, 0 PD, to a point at a PD of V. So that is energy stored. And there's a question, that's why I'm trying to give this definition. Energy stored is the work done in charging or discharging a capacitor from a zero potential difference to a potential difference of V. When we say V, it means it can be any value. You can charge from 0 to 1, you can charge from 0 to 20. That's why we are saying V, which is variable. So, and there's a question that was asked here also. Remember, your exam would not just be about calculation. So the question says, the capacitor stores energy charging the capacitor. Option B, charging the battery. Option C, storing the charge. Option D, lifting a cooler of charge. So drop the answer if you know. I'll read it again. And you drop your answer, type it. Type your answer, let's see, from what we've explained. Capacitor stores energy. And this energy is equal to the work done in doing what? That is what the question is asking. A capacitor stores energy, we know. And then this energy is equal to work done in doing what? Option A, in charging the capacitor. Option B, in charging the battery. Option C, storing charge. Option D, lifting a cooler of charge. Any answer?
Kemjika said A.
A, thank you.
Duru, A.
Thank you.
22 of them.
So that is what we have explained. The energy stored is the work done in charging the capacitor. That is it. So you can see how exam can come from definitions they would ask. And what is the formula for energy stored or work done by a capacitor? It is given by U. We have three formulas. Equals half CV squared. This is the formula where C is capacitance, V is voltage or potential difference. Then we also have U equals half QV. We have this. And we also have U equals half Q squared over C. So these are formulas for energy stored by a capacitor. So any one of them can work. Once you have this formula and you have Q equals CV, you don't even need other formulas. But why am I giving you these three formulas? Exam can ask you, which one of the following does not represent energy stored by a capacitor? They will write this as option A. They'll write this as option A, write this as option B, write this as C, then put a wrong one as D. So these are all formulas for energy stored by a capacitor. Now we also have what we call energy density. Energy density. Energy density. So energy density is actually energy per unit volume. Energy per unit volume is what you refer to as energy density. So for that, we usually use small letter U, but since my hand may not be able to differentiate, I'll just use U and a subscript of D, telling you that this is energy density. So what is the formula for energy density? Energy density is half epsilon naught E squared, where in this case, E is actually what you know as electric field. Electric field intensity. So it's electric field intensity. So that is the formula for energy density. What is the unit of energy density? The unit is joule per meter cube. joule per meter cube. That is the unit of energy density. So these are formulas you should know also. And then finally, before we now look at maybe one or two problems, finally, dielectric materials. Now, what are dielectric materials? Dielectric materials are insulating materials that are inserted between the plates of a capacitor. I'll repeat, dielectric materials are insulating materials that are inserted between the plates of a capacitor. I hope that is clear. Now, these materials can insulate electric current, but they don't insulate electric field. These materials can insulate electric current, but they don't insulate electric field. So what it means is that current cannot flow through them, but the electric field can be transmitted through them. That is why they are special. Instead of calling them insulators, you call them dielectric, right? Because it has extra features that allows the electric field to be transmitted. So I believe that explanation is clear to you. Now, one of the things you should know about dielectrics is that dielectrics increases the capacitance of the capacitor. The presence of dielectric increases the capacitance of the capacitor. So if I have a capacitor A, these are the plates of my capacitor, and I have the medium that separates these two plates. The medium is air, and I have capacitor B. These are the plates of my capacitor B, and inside I have dielectric material. So which of these two capacitors would have a higher capacitance? Of course, this one that has a dielectric material. Air is a dielectric material, but is actually the least dielectric material that is known. So this one will have a higher capacitance. So dielectric materials increases the capacitance of a parallel plate capacitor. So that is worthy of note. So what is the relationship? The capacitance C with dielectric. Capacitance when there is a dielectric, that is in the case of B, when there is a dielectric, is equal to K times the capacitance when there is no dielectric. So you should take note of this. C is capacitance with dielectric. C is capacitance when there is a dielectric. C naught is capacitance in free space when there is no dielectric, or when the dielectric is air. That is C. Now, exam can ask you that the ratio of capacitance with dielectric to capacitance in free space is known as what? The ratio of capacitance with dielectric to capacitance in free space is known as what? Give me the answer before I explain it. The ratio of capacitance with dielectric to capacitance in free space is known as what? Who has the answer?
Not you, no answer.
Okay. All right. This ratio is known as dielectric constant. Now, if I make K the subject, K is equal to C over C naught. So this is capacitance with dielectric. This is capacitance with free space. So this ratio is known as K. And K is what? Known as dielectric constant. K is called dielectric constant. For air, if you are dealing with air or free space, then it means that K is approximately 1. So for air or free space, the electric constant is equal to what? 1. That is also a question I saw here also. They said that the dielectric constant of air is practically taken as option A, more than unity. Remember, unity means 1. So option A says more than unity. Option B says unity, which is this. Option C says less than unity. Option D says 0. The dielectric constant of air is practically taken as what? It's taken as 1. So you should take note of that. So this is what you need to know. Also, I want to mention a second point for dielectric still. In terms of electric field intensity, electric field, remember dielectric increases capacitance, but for electric field, dielectric decreases electric field. Dielectric materials decreases electric field. Please take note of this. These are the things you'll be seeing in exam. Dielectric increases capacitance, but it decreases electric field. Of course, when you decrease electric field, you will increase the capacitance. So what is the relationship? E is equal to E naught over K. This is the relationship for electric field. So you can see that the electric field with a dielectric material is going to be that in free space divided by some number, which obviously this should be small because you're dividing this to get this. So it decreases electric field. And then finally for PD, for potential difference, dielectric materials decreases PD. So it decreases voltage, or you can say it decreases potential difference. So with this, I think I've summarized capacitors. And what is the relationship? V is V naught over K. So you should know these things. Let me see what I have one question to solve and we'll move to DC. So I have this question that says the dimensions, I'm going to write it. I'll take just 2 problems, 2, and we move. So how many persons are present now? Let's see whether you are sharing. You need to share 30. So you need to share this. Remember your exam, you need your friends to pass this exam. So share. The dimension of the plates of a parallel plate capacitor are 8 cm and they are separated by a distance of 2 millimeters. Calculate the capacitance if question I, air is between the plates. Question I, glass of dielectric constant 5 fills the space. The electric constant fills 5 fills the space. So quickly solve this. I'll give you 30 seconds to solve. Let me refill my marker. So solve this. Any answer? All right. Do we have answers now?
Yes.
Okay. Tell me.
Charles. Says,
Charles.
yeah, number 1, 8.9.
Number 1 is 8.9. Do I have options? Okay, I don't have options there. Number 1, 8.9.
Yes, e raised to the power minus
8.9 finish.
e raised to the power minus 11.
Times 10 to the power minus 11. All right.
Yeah.
All right. What about number 2?
Then
Is it the only one that's produced answer?
Yes.
Okay.
4.45
4.45
times 10 raised to the power minus 10.
minus 10. Okay. Only him.
Yes.
Okay. I'll give you one more second, then I'll solve. All right. I think I will be solving. Any other answer?
Yes.
Okay.
Lutana air 28.32.
Okay.
Then-
28.32.
Yes.
0.32. Okay.
Yes. Then for glass 141.6.
Okay, let's solve. Let's make do with this answer. Now let's solve and save the time. Now they said the dimensions of the plates. The dimensions would help you get area. The dimensions of the plates of a parallel plate capacitors are 8 cm. So if they say the dimensions are 8 cm, it simply means it is a square plate. 8 cm of length, 8 cm of breadth. That is what it means because they gave you only one value. So it means it's a square plate. So first, the length of the plate is 8 cm, which I'll divide by 100. This will give me what? 0.08 meters. So for a square, the area of a square is L squared, which is 0.08 squared. So give me this answer.
0.0064. That is 6.4 times 10 raised to the power minus 3.
Times 10 to the power minus 3 meters squared. So this is the first thing you want to do. Now they said the plates are separated by a distance of 2 millimeter. The distance is 2 millimeter. We can't work with this. We have to change. So this is going to be 2 milli means 10 to the power minus 3. So once you see milli, you change it to 10 to the power minus 3. So we have that. And they said calculate the capacitance if air is between the plates. That's the first case, which is simple. And when you are considering air, the capacitance we usually denote with C naught, which is going to be epsilon naught A over what? Over D. So with this, we can get what we need, which is very straightforward. So I have that the capacitance C naught is going to be 8.85 times 10 to the power minus 12. That is the value of epsilon times the area, 6.4 times 10 to the power minus 3 divided by the distance, which is 2 times 10 to the power minus 3. So quickly, 10 to the power minus 3 can go. So 2 in this is 3.2. 3.2 times 8.85 quickly. 3.2 times 8.85. What do we have?
3.2 times 28.32.
28.32 times 10 to the power minus 12. So this is what we have. This person got it, but he didn't give me power. Except he wrote it there. So this is what we have. This is the capacitance in free space. This is the capacitance. Now, we want to get the capacitance. They said if glass of the electric constant 5 is between it. Now we know that under this capacitance is C, and which is equal to K, the electric constant times C naught. So quickly, since we've gotten C naught, I'll just use K, which is 5. 5 times C naught, which is 28.32 times 10 to the power minus 12. So if I solve this, I would have what?
141.6 times 10 to the power minus 12.
141.6 times 10 to the power minus 12. This is farad, this is farad, this is farad. So this is our answer. Of course, 10 to the power minus 12, what do we call it? Remember, 10 to the power minus 6 is micro, minus 9 is nano, minus 12 is what? Pico. So I can replace this as picofarad, that is minus 12. You can see that in your option tomorrow. So I believe this is clear. Did anybody actually get it again?
No.
No. All right. So quickly screenshots. If you want me to move on, say move. If you want me to wait, say wait, so that you copy fast. Tell me which one to do so that we can move.
Kenjika got it.
Kenjika got it. Okay. I love that.
Move on.
I should move on, right?
Yes.
Thank you. So I think we are done with capacitors. So let's save the time. Let's get to direct current. I've summarized capacitors already. So we want to look at DC direct current. Let's say we combine two topics quickly. Current, electricity, and DC. So we combine these two. Now quickly, what is current electricity? Current electricity is also known as dynamic electricity. So whenever you hear the word dynamic, it means something that is changing. So current electricity is the study of electricity with moving charges. Current electricity is the study of electricity with moving charges, or is the study of flowing current, right? That is current electricity. Then direct current is a current that flows in only one direction. Remember, we have two types of current based on direction of flow. We have direct current, DC, and then we have alternating current, AC. But we want to consider the direct current, but still on current electricity. Remember, current electricity is the study of moving charges, while the study of stationary charges is known as what? Who can tell me? If the study of moving charges is known as current electricity, then the study of stationary charges is known as what? Put the answer if you know it while I continue. Now, when you're studying...
Electrostatics, innocent.
Thank you, innocent. Electrostatics, that is correct. Now, quickly, now when you say moving charges, movement of charges is actually known as current. Movement of charge is known as what? Current. So it means that if we want to define charge, we can first current. If we want to define current, we would say that current is a result of the movement of what? Charges. So electric current is the charge that flows through a unit area per second. That is current. The number of charges flowing through a cross section of a wire per second. That is electric charge, right? Now, an electric current is denoted by the symbol I and is given by the relation Q over T. Is current. I is Q over T. So current are the number of charges flowing through a cross-sectional area of a wire in 1 second. So this is the formula. Now you should know that electric current actually flows in opposite direction of the electron. This is an exam question. They will ask you, current in a circuit flows in what direction? Option A, in the direction of electron. That is wrong. Electric current flows in the direction opposite to the flow of electrons. Or you can say it flows in the direction of a positive charge in a conductor. So you should know that. Now, which means that electrons flow from negative part of a battery, while current flows from positive side. So if I have a circuit like this is a battery. I have this, and this is a wire. It means that current would flow this way, in this direction, while electrons would flow in this direction. So you should take note of this as exam question. So now this is electric current. Now, if you consider a large wire like this that has an area, of course, you should know that the area of a wire is actually the cross section, which is same as the area of a circle. That is the area we always refer to for area of wire. So anytime you're dealing with wire and you have to deal with anything concerning area, you should know it's area of a circle. So the current that flows through a wire of length L, if a wire has a length of L, the current that will flow through that wire is given as I, or let's say I over A equals NE times VD. So that you should know that I over area, or let's say if I make I the subject, I can just say I is equal to NE VD times area. So this is the current that would flow through a wire of length L. That's the amount of current that will flow through it, where N is actually the volume density. N is actually the volume density. So it means that this quantity NE, the unit, remember the unit of charge is what? Coulomb. So it means that the unit of this quantity NE is going to be coulomb per unit per meter cube. So NE, the unit, is coulomb per meter cube. So this is charge density N. So the unit of this product is coulomb per meter cube. So it simply means that NE, the unit of only N, is what? Per meter cube, charge per meter cube. So you should take note of that. So this is how you can find current, where VD, V subscript D, is called drift velocity. That is the velocity with which the electrons would move in this wire. The electrons, the drift velocity. Then A is the cross-sectional area of the wire. Is cross-section, and the cross-sectional area of the wire is actually pi r squared. As area of a circle, pi r squared. Now, somebody may ask, what about this formula you wrote, I over A? Please take note that I over A is given by the symbol J, and J is called current density. J is called current density. So they ask you tomorrow to find current density. You should know it's going to be current over area, right? That's current density. Take note of this before I move on. And these are basically what we should know under current electricity. So I want to switch over to direct current. So screenshot this so that I can rub. These formulas are very important. Very important. Let me see, I can find one quick question there and we move on. So screenshot that. Okay. Okay, now let's take this simple problem. So I think I can rub this. So the question says, near the earth, the density of protons in the solar wind is 8.7 times 10 to the power 6 per meter cube, and their speed is 4.7 times 10 to the power 5 meter per second. So we said find the current density. Find the current density. So I'll give you 30 seconds to solve this. Find the current density. Find the current density. Okay, find the current density. So any answer?
No.
Okay. I think I should solve and save our time. Any answer?
Chukwuemeka.
Chukwuemeka, I love the fact that you are always producing results. Thank you.
4.089.
Okay,
Nice.
4.089
089.
times 10 to the power
12.
12. Okay, now let me solve and save time. I need to summarize. It's already 1 hour, I think. Now, we have that near the Earth, the density of protons, we're dealing with protons, in the solar wind is this. You can see per meter cube. So it means they gave us N as 8.7 times 10 to the power 6 per meter cube. And their speed, that is their drift velocity, is 4.7 times 10 to the power 5 meter per second. So find the current density. Now we know that current density is J, which is going to be what now? Going to be NEVD. So with this, we can find it. So very quickly, I know that J is going to be N, which is 8.7 times 10 to the power 6. E is charge of electron or proton, because they have the same charge, which is 1.6 times 10 to the power minus 19. Then VD is 4.7 times 10 to the power 5. So if you punch this, you'll have what? You'll have, so just punch 7 times 1.6 times 4.7.
65.424.
65.424. Finish.
Yes.
No power.
Yes.
Okay.
That is for.
Okay, when you multiply these things,
Yes.
okay, the power is going to be 11 minus 19, which is what? Minus times 10 to the power
8.
minus 8. So, and the unit is ampere per meter square. That is the unit of current density, ampere per meter square. So who got it? Nobody got it.
Yeah.
Nobody got it.
Yeah.
Oh, it's unfortunate. Now there's a second part to that question. The second part says, if the Earth's magnetic field did not deflect them, the protons would strike the Earth. What total current will the Earth receive? So they are just asking for what will the total current be in this case. What total current will it receive? Do we have sufficient information to find the total current? Now we know that, okay, I over A is equal to J, right?
Yes.
Yes. So it means I is going to be J times area. So, but we don't have information for the area. So I think there's an omission there. So because we know J, but we don't have information for the area. So I think they are supposed to give us area of that solar system for the wind system. So let's leave it this way. But under exam condition, you already know J, and you have information, you have the area, you can find the area. So let me quickly move. I believe I can rub this now, right? So let's look at DC. So remember we said that direct current is current that flows in only one direction, right? That's direct current. And the major law that governs direct current is Ohm's law. Ohm's law. That is the major law that governs direct current. And according to Ohm's law, if I should state it, Ohm's law says that the current flowing through a metallic conductor is proportional to the potential difference across its ends, provided that temperature and other physical constraints are kept constant. So I believe that you already know Ohm's law. I'm just stating for stating's sake. The current that flows through a metallic conductor is proportional to the potential difference across the terminals, provided that temperature and other physical constraints are kept constant. So mathematically, we can say that Ohm's law is V equals IR. So this is Ohm's law. Now you should know that another version of Ohm's law, in as much as this is the relation for Ohm's law can still be written as this. So this is still another version of Ohm's law. So exam can ask you, one of the following is not a, in fact, this is still another version for Ohm's law, J equals NEVD. So this is still another version. Exam can ask you which of these is not equal to or is not a form of Ohm's law. So these three things you can see are forms of Ohm's law. So they are all Ohm's law, right? So if that is the case, it means you know Ohm's law. Take note of it. So from this first relation, V is voltage, or what you know as potential difference, I is current, then R is resistance. Then you also know from this second relation that J is current density. J is current density, which I've given you already, current over area. Then this symbol, sigma, this symbol represents conductivity. So it is called conductivity. Conductivity. That's what the symbol is. And it has a formula which is 1 over this. So conductivity is the inverse of resistivity. So this is actually called resistivity. So you should take note of these relations. So we already see, you've seen this formula already. Now, where E is electric field intensity. Electric field intensity. That is E. So you should take note of these things. Then also, what is resistance? You should know that resistance is the opposition to the flow of current through a conductor. And the resistance of a conductor is dependent on 3 factors. Resistance of a conductor, I can rub this, just try to screenshot. So resistance of a conductor is dependent on 3 factors. Resistance is dependent on 3 factors. Number 1 factor, the length. Resistance is dependent on length of the conductor. So if I have 2 wires like this is 1 wire and this is another wire. Which of these 2 wires would have a higher resistance? This one, because it is longer. So resistance is dependent on length of conductor. That is 1. Number 2, resistance is dependent on cross-sectional area of the conductor. Cross-sectional area, that is area. So it's dependent on, so it means that the thicker the wire, the smaller the what? The resistance. I'll still give the relationship. Then number 3 is resistivity. Resistivity, which is known as the nature or property of the material. So that is to say, resistance depends on length, depends on cross-sectional area, and depends on the property of the material. That is to say, copper, when you compare copper wire, for example, and you compare it to aluminum wire, their resistance is not the same. Which of them has a higher resistance? Aluminum has higher resistance than copper. And that name, aluminum, is a property which affects the resistivity. So resistivity depends on the property, the nature of the material. So these are things that affect resistance of a wire. What is the mathematical connection between these things? The resistance R is rho L over A. Is the formula. So you can see that as the length of the wire increases, the resistance will increase. As the cross-sectional area decreases, resistance will increase. So it's inverse. As the cross-sectional area decreases, resistance will increase. In exam, they may decide to confuse you. Instead of telling you as area decreases or as area increases, they will ask you as the thickness of the wire increases. So you should know that area means thickness. So if the thickness of the wire increases, it means that the area increases. If the thickness of the wire decreases, it means that area does what? Decreases. So that can now affect your resistance. So the thicker the wire, the smaller the resistance. The thicker the wire, the smaller the resistance. Take note of it. So this is the relationship for resistance. So I'm trying to be fast this time because I want to hit at least Kirchhoff before we now end this. I know it's already past our agreed time, but let's quickly do. So how many persons do we still have on board?
38.
38. So okay, please, if you have not liked the video, please do well to like this video. I can see few likes. How many likes do we have?
24.
24. We have 38 people. So some of you have not liked the video. Click like, and continue. That is your way of supporting this. Like the video so that we can get equivalent number of likes to the number of people that are on board. Now, quickly, we want to look at arrangement of resistors. How do you arrange resistors? I won't waste time there because it's similar to capacitors. So resistors can be arranged in series. So, and also in parallel. Let's look at series. For series arrangement of resistors, you have like this. This is the symbol for a resistor. So if I have something like this, then it means resistors R1 and R2 are arranged in series. I believe you know this already. So these resistors are in series. When you connect them straight, they are in series. The same diagram for capacitors in series. What is different is the formula, not the diagram. The diagram for series resistors and series capacitors is the same. What differentiates them is their formula. So how do we find equivalent resistance for series? The equivalent is just going to be the addition, the direct addition when they're in series. So also, we can also, before we talk about parallel, we want to point out two things here. So there are 2 points you should note. What are the 2 points you should note? When resistors are in series, current is the same. Number one, current is same. So that is to say, current in R1 is the same current in R2. Current is what? The same. When resistors are in series, number two, voltage is different. Voltage is different. So these are 2 important points you should note for resistor arrangement. Now, we want to look at 2 parallel arrangements. Parallel. Now, how do you connect resistors in parallel? You have them like this. Like this. So these resistors, R1, R2, these resistors are connected in parallel. Remember that this can also be the symbol of a resistor. This can also be the symbol, so that anyone that is used in exam, you will not be confused about it. Now, how do we get equivalent resistance when resistors are in parallel? The equivalent is 1 over R equivalent equals 1 over R1 plus 1 over R2. This is equivalent when you have them in parallel. Now, when you're considering only 2 resistors in parallel, the shortcut for finding it, when you have only 2 resistors, the shortcut is product. Product over what? Sum. I will give you a quick one, and you tell me the answer. Before that, let's still point out 2 points important for parallel. So what are the 2 points important? For parallel arrangement, voltage is same. Voltage is the same. That is number 1. Number 2, current. Current is different. Please take note of these things. That is where your solution to questions come from. For parallel arrangement, voltage is the same. So the voltage in this place is the same voltage in this place, which is actually the total voltage. But current is different for parallel arrangement. So I believe this is really clear to you. Now, if you understand, tell me how, I will give you a question, how will 2 resistors of values 2 ohm and 3 ohms each be connected so that it gives a high effective resistance. So that it gives a high effective resistance. I believe you should have dropped the answer already because it's very simple. Now,
Chukwuemeka series.
Chukwuemeka said is what?
Series.
Series. They should be connected in series. Who else?
No.
All right, now let's answer it quickly. How will you connect two resistors and the value of one of them? R1 is 2 ohms, R2 is 3 ohms. How will you connect it? If you want the equivalent value to be high, we are going to test since we are solving. So we have two arrangements, series and parallel. Let's see which arrangement will give us a higher value of effective resistance. So for series, let's start with series. For series, the effective or equivalent is going to be R1 plus R2. So for series, I'm going to add them up. 2 plus 3, which is what? 5 ohms. So you can see that this is 5, which is bigger than 2 and is bigger than 3. Let's check for parallel. For parallel, the equivalent, remember I told you when you have only two resistors in parallel, you do product over sum. So for parallel, I'll have product 2 times 3 over 2 plus 3. Give me the answer. 6 over 5. Give me the answer. 1.5 ohms. 1.2 ohms. So which one gives us a higher value? You can see it's 5, which is series. So it means that anytime, not just for this question, anytime you want to get a higher effective value, you must always do an arrangement in what? In series, not parallel. So you should take note of this. Now screenshot it so that I can move on.
So someone is saying you should touch AC circuits, DC circuits, modern physics.
Okay. Okay, you are suggesting I should touch what? AC circuits.
DC circuits.
This DC we are doing already.
Modern physics.
Okay, can I rub this? Now, tell me, do you want me to do Kirchhoff very fast or I should leave it? Drop your answer or I should leave to AC. Just pick one of them. Kirchhoff or AC. I'll know the next to quickly handle. Kirchhoff or AC. Choose one. Since you are suggesting AC, let's know where to move to. All of you drop your suggestion, Kirchhoff or AC. So tell me quickly so that I will know which to go to next. Any answer yet?
Kirchhoff.
Kirchhoff 1. Who else?
Kirchhoff, I'm seeing that.
Only one person and everybody saying Kirchhoff.
About 4 persons are saying Kirchhoff.
So Kirchhoff takes it. Of course, right?
Yeah.
That is the highest. So quickly, let's look at Kirchhoff. Kirchhoff's law. Now, Kirchhoff's law, of course, I'll finish it now. Kirchhoff's law is divided into 2. So we have number 1, KCL, which is known as Kirchhoff's current law. Number 1 is what? Kirchhoff's current law, which you can also call Kirchhoff junction rule. Is it that you call it Kirchhoff current law or you call it Kirchhoff junction rule? That is the first law. Now, what is KCL? KCL says that the total current going into a junction equals the total current leaving the junction. That is KCL. The total current entering a junction equals the total current leaving the junction. That is one way you can say it. Or you can say the net sum of current at a junction is 0. The net sum of current at a junction is 0. So this is the mathematical way of writing it. The net current at a junction is 0. So that is number 1 Kirchhoff's law, KCL. Now, another thing you should know is that KCL is derived from the law of conservation of charge. From the law of conservation. This is an exam question. Conservation of charge. So that is where KCL is derived from. Then, now when you say KCL, before I look at the second law, let's see what it means. A junction, remember KCL says that the total current going into a junction equals the total current leaving the junction. So what you want to ask yourself is, what is a junction? A junction is a point where 3 or more wires meet. A junction is a point where 3 or more wires meet. So you can see that this is a junction because I have 1 wire, 2 wire, 3, and 4 wires. So a junction is where 3 or more wires meet. So while this is a junction, if I have something like this, can I call this point a junction? This point is not qualified to be called a junction because it's only 2 wires that are meeting here. So a junction is where 3 or more wires meet. Now let's apply KCL here. Let me give you a question. Say this is I, this is 2 ampere, this is 3 ampere, this is 5 ampere. Find I. So drop the answer quickly so that we can move on. Drop the answer, find I, applying KCL. Who has the answer?
Okay.
I'm waiting. Who has the answer? Nobody.
Yes.
Nobody yet.
Yes.
Okay. Now I'm solving to save our time. To solve this, remember KCL say the total current entering a junction. So this is our junction. What current is going into it? You see that I is going there. So I would say I. Which other one is going there? You see that 5 is going there. So I would say plus 5 would be equal to the current that is leaving. So you see that 3 is leaving. So I would say 3 plus 2 is also leaving. I would say 2. So that I have that I 5, 3 plus 2 is 5. When this 5 crosses, you have minus 5. So I becomes what? 0. Now this brings us to a very important thing to note about KCL. Now, if you look at this diagram, you would see clearly that at every point in time, current is either leaving the junction or entering. But what is the net current? Okay, this is just I. Okay, this is just I. It didn't really explain what I wanted to explain. But I is actually 0. That is just what it is. So it means, in actual sense, you have this. So what I was trying to explain is that at every point in time, there is current at a junction. But at every point in time, there is no net current at a junction. Take note of that. At every point in time, there is current at a junction. Is either current is coming in or current is leaving in. There is no time where there is no current. So, but at every point in time, there is 0 net current. Take note of that. So that is the first Kirchhoff rule, KCL. Number 2 is KVL, Kirchhoff's voltage rule. That is number 2, KVL, which you can also call Kirchhoff loop rule. You call it KVL, Kirchhoff voltage law, or KVL, Kirchhoff's loop rule, right? Yes. Now, what does KVL say? KVL says that the net voltage and EMF at within a loop is 0. The net sum of voltage and EMF within a loop is 0. Net sum of EMF and voltage drop across a loop is 0. That is it. Or you can say the net sum of EMF equals the net sum of voltage drop across the loop. So you can say it in any of these 2 ways. Now, what's the difference between EMF and voltage drop? EMF is battery voltage. Voltage drop is the product of current and resistance. So if I have something like this, if I have a circuit like this, and say this is 12 volts, this is R, and I have a current flowing. What is the EMF in this circuit? The EMF in this circuit is 12 volts. That is the battery voltage. Or what is the voltage drop? It's going to be the current times this resistance. So voltage drop is IR. So take note of that. So that is KVL. Now, remember we said that KCL is derived from the law of conservation of charge. Then the same way, KVL is derived from the law of conservation of energy. KVL is derived from the law of conservation of energy. KVL is derived from the law of conservation of energy, and this is all for Kirchhoff's law. So we want to apply it to solving a problem. So I will just go straight to an example that would help us fast. Remember, there is sign convention for this, but let me just go straight and do it in this example. So say we have this circuit. So this is 3 ohms, this is 1 ohm, this is 2 ohm, this is 6 volts, this is 3 volts. So I have my current here, all this I2, all this I1, all this I3. So I have my currents like this. So I should have made my diagrams. The question says find I1, I2, and I3. So that is what we want to find in this. So we're going to apply KVL, KCL, and KVL. So let's start. And first, you notice that this point is a junction. And if this is a junction, you have this current I1 is going to this junction, while I2 is also going to this junction, but I3 is leaving the junction. So applying KCL, I would have that I3, which is leaving, is equal to I1 plus what? I2. I1 is entering, I2 is entering, so I will add them up, is equal to I3, which is leaving. So if I should arrange this, I can still write this as I1 plus I2. When this one comes, it becomes minus I3 equal to 0. I'll call this equation 1. So I have this. Now the next thing I want to apply, please follow me. Try to follow me, right? Those of you that are watching, so that you understand. I want to apply KVL. This is loop 1. In exam, they will give us loop directions. So let's say we have this loop direction. Now, how to apply KVL is when you are considering any particular loop. I have 2 loops here. I have this and I have this. When you are considering any particular loop, you make sure you go round, touching all the elements in that loop. In this first loop, I have how many elements? 3 elements. In this loop, I have this, and I have this. 3 elements. When I come down to the second loop, I have how many elements? I have 4. I have this, and this. So we're starting with this up loop. Now let's see. And let's say we are following our loop direction. See how our loop is going. Our loop is moving in anti-clockwise and clockwise direction, right?
Yes.
This clockwise.
Yeah.
So if your loop comes out from the positive part of your battery, the long side of your battery is positive. If your loop comes out from the positive side, then that EMF is positive. So if you look at this, this is our loop direction. Our loop is going this way. So it's going to enter from the short one, and then it will come out from the long one. So it means that this EMF is going to be positive 3. Now I would continue. I've touched this. This is the only one I've touched. I will go and turn around. I'm coming like this. For this one, my loop is going forward. You can see the direction forward. If your loop and your current are in the same direction, the voltage drop will be negative. So you can see our current is going forward. Our loop is also going forward for this case. So it means my voltage drop is this current times this, which is negative. So I would say negative 3 times I3. Now I've touched this one. I've touched this, is remaining this. Now for this one, the current, which is I2, is going forward. But the loop is also going forward. This is our loop. This is our loop, which is going forward. And current is also forward. So it means this is also going to be negative. Negative 1 times I2, which is I2. And there's no other thing in this loop. I've touched this, this, and this. So I would equate to 0. Right? Now, let me rearrange this well, because I'm trying to save time. If I'm to rearrange this, I can just say I2 plus 3 I3 equals 3. This is equation 2. Check it very well, you would see. Then finally, for the second loop, I will want you to give me the equation for the second loop fast. I want to see who has it. I'm waiting for your answer so that I can move. So I'm waiting. Who would get the equation for the second loop? Anybody?
Not yet.
I'm waiting. I'm giving you 5 seconds. Generate the equation for the second loop. That's the last thing we need. What would it be? Nobody yet? You can just look at it and actually get the answer.
Okay.
Anybody?
Yeah.
Okay.
Nkemjika said plus 2I1
Okay.
plus I2.
Put Nkemjika's answer only in a box and then I'll solve. Minus what?
Minus 2I1
Uh-huh.
plus I2
Plus I2
equals to minus 6.
equal to minus 6. This for Nkemjika, not my own. I'll solve my own now.
Chukwemeka said I2 minus 2I1
which is same
equals to minus 3.
Minus 3. Okay. Yeah, it's now different. Okay.
Then Okuma said 2I1 minus I2 equals 6.
Okay, same as this actually. Okay.
Yeah. But the other one's own has minus in.
Okay, thank you. Let's do it together. Let's do it together. Remember, my loop is still clockwise. So let's start with this part. So my loop is going this way, clockwise. Clockwise. So please take note. Now, if I'm moving, I'm following my loop direction. It means I'm moving forward. My loop would come out from the long terminal, which is positive 6 for this case. Now I'll go and turn. My loop would be going this way now. For this one, my loop is going this way. So meaning my loop is coming out from the short terminal, which is negative. So I would say minus 3. Then I will continue. My loop is moving forward. You can see it. My loop current, which is I2, is coming backward, opposite, right? Current is back, loop is forward. So opposite direction is positive. So I'll say plus 1 times I2, which is I2. Then I have this one left. So for this one, my loop is also moving like this. You can see it. My loop is going backward. Current is also going backward. So it's negative. So it's negative.
Yes, about to go.
How many percent?
It's going, it's reading 30 seconds.
Okay, let me get that. It didn't go. Yeah. Okay. Sorry, my battery almost disappointed us. Thank God for power bank. So let me repeat this last part. Is okay, right?
Yeah.
So this, for this particular one now, so I have my loop is forward and then the current is also forward. So the voltage drop here is negative. So which is going to be negative 2I1, and we are done. We've considered this, we've considered this, we've considered this and this. So we can 6 minus 3 is 3 plus I2 minus 2I1 equals 0. So if I'm to arrange this, I would have 2I1 minus I2, right? Yes, equal to 3. This equation 3.
Minus 2I1.
What I did was I moved this to this side, so it became plus. This one followed it, it became minus. I left this one here. So this is what you would have at the end. So who got it? So obviously this one is not correct because of this constant. So my 3 equations are this one, this, and this, which I'm not going to solve. So if you have your calculator, I've taught you, some of you that attended our physical class, I've taught you how to solve simultaneous equation with calculator. And that is what the exam will require from you. Solving these 3 equations, 1, 2, and 3. Solve them simultaneously. Then you will get the values of the current, right? Has anybody solved it? Somebody should punch it and give us the answer. Somebody that has calculator close by should use calculator and solve the simultaneous equation 1, 2, and 3 and give us the answer, because we are done with Kirchhoff. I will just explain one or two things under AC and end this video. How many persons are still alive?
33.
33. How many likes?
38.
38. That is good. Has anybody gotten the answers?
Not yet.
Not yet. So I'll be moving on. I'll be moving on to AC circuit. Remember, alternating current. AC means alternating current. Alternating current is current that reverses direction with time. Alternating current is current that reverses direction with time. And alternating current, since it changes direction, it means that if you want to show it in a graph, you're going to use something like this. See how it changes direction with time. So this is the graph of an alternating current. This kind of graph is referred to as sinusoidal graph. So it's called sinusoidal. So exam can ask you, the graph of an AC is one of the following: A, sinusoidal; B, straight line; C, you would see so many other things. So the graph of an AC current is what? Sinusoidal. So it is either it is like this, or it is this way, or is this way. Both of them are still sinusoidal. The only difference is that this one represents a sine graph, while this one represents a cosine graph. So that alternating current, the graph of an alternating current is sinusoidal. Even though I didn't mention for DC, but the graph for a DC is constant, it's a straight line. This is how it is. This is the graph for a DC, constant. Now, there are certain terms you should know when you are dealing with alternating current or AC current. Terms you should know. Number one is what you call instantaneous voltage or current. When you are talking of AC, AC does not just refer to current, it refers to current and voltage. So one thing you should know is instantaneous values, which would refer to instantaneous voltage or current. Instantaneous values are the values of voltage and current at a particular point in time. Say they want you to find current at 2 seconds, that is instantaneous. Find current at 10 seconds, that is instantaneous at a given time. And the equation for that is I equals I naught sine omega t. And then for voltage is V equals V naught sine omega t. If they don't use this equation, they don't use sine, they can use cosine. So you can have I equals I naught cos omega t. You can have V equals V naught cos omega t. So any of these two equations, set of equations, is correct for instantaneous values of voltage and current. I hope you're following. How many do we have there? How many
29.
29. 31. All right. Now, so this is instantaneous. These are terms you should know. Now, they can give you a question in an exam like this. Say I equals 3 sine, let's say, omega t. Say find the peak current. Find the peak current. I didn't mention, but you should know that I naught in this formula represents peak current, V naught represents peak voltage. Peak means maximum or highest. So if you want to find, they give you an equation like this, say find peak current, you just compare it. This thing, anything behind sine represents the peak. So our peak current is going to be 3 ampere. So that is our peak current. So exam would come this simple way, which you should know. Now we're talking about the terms, instantaneous current and voltage. Number 2 term you should know is peak value. Peak value is the highest or maximum value of current and voltage you can obtain, which you can see how we find it, right? Yes. Number 2 we said is peak. Number 3 is RMS. RMS values. RMS are the DC values that are equivalent to an AC. RMS are what? DC values that are equivalent to an AC. So it means if I have an AC, I want to get the equivalent value of, I want to convert that AC to DC. When I convert an AC to DC, that DC would now be called RMS value. That's what it means. So RMS has a formula, which is IRMS is equal to maximum over root 2, or VRMS is equal to maximum voltage over root 2. So these are formulas for RMS that you should know. And then, of course, you know that even if you don't want to use this root 2, you can still say RMS is equal to 0.707 I naught. Same thing for VRMS, right? So you can always find this. Then power and AC circuits. Power is given as, power is the rate at which energy is dissipated. Power is the rate at which energy is dissipated or consumed in a circuit. And power is given as IRMS, VRMS. Power is also given as IRMS square times R. Power is also given as VRMS square over R. So these are formulas for power in terms of RMS values. You can also have power in terms of peak values, which would be given as power P is 1 over 2 I naught V naught, or power equals 1 over 2 I naught square R, or power equals V naught square over R. So these are formulas for power in terms of peak value. So any of those two you use, you get the answer. Let me give you one question that would summarize all these things we have done so far, and we will move on and draw a conclusion, because I will be ending the class very soon. So I have okay, I have this question. Okay. An AC, I hope the video is still clear.
Yeah.
An AC flows through a resistor of 5 ohms. Heat is dissipated. I'm trying to shorten the question. Heat is dissipated at the rate of 20 watts. What is question I, the RMS current, II, the peak current, III, the RMS voltage, IV, the peak voltage. So these 4 things I will solve quickly, and then that will explain what we have said so far. Now, the question says an AC flows through a resistor, and they gave us resistance R of 5 ohms, and heat is dissipated at the rate of this. Now remember, watt stands for power, so the unit of power is watt. So they gave us power of 20 watts. And the question says, what is RMS current? Now, first, we know that power P is given as IRMS squared times R. This is the formula for power in terms of RMS. So it means if I want to find the RMS current, I would quickly do IRMS square would be equal to P over R. So that IRMS would be square root of P over R, which is square root of 20 over 5. 20 over 5 is 4, and square root of 4 is 2 ampere. So this is the RMS current. Did anybody get it?
Yeah, Destiny.
Destiny, Ikechukwu. They are just coming online.
Destiny and TK.
Chike.
Chisom got it.
Okay, Chike Chisom, thank you. Destiny is just coming online because I know I should have been seeing your answer before now. So copy your screenshot. I want to rub this so I have space. And the second part of the question, the second part says we should find the peak current. Everybody should be able to solve this. You know that IRMS is equal to peak over root 2. So what it means is that peak current is going to be root 2 times RMS current, which is actually going to be root 2 times RMS 2. Our answer will be what? 2.83 ampere. So who got this? Because I expect that you should have produced the answers.
Innocent got it.
Innocent got it.
Nkemjika.
Destiny. Thank you. So tell me the answer to the third one before I solve.
NECO got this one too.
Okay. Anybody has produced the answer to the third?
No.
Okay. All right, let me solve the third one because I need to tidy up this video. So RMS voltage, you should know that RMS voltage is RMS current times resistance. So I have my RMS current as 2 times my resistance of 5, which is what? 10 volts. That is the third question. Then the last one says peak voltage. Also, peak voltage is peak current times R. So you can also get it from here. Did anybody produce the RMS voltage?
Yes.
Okay.
Innocent.
Did you get it?
Yes.
Okay. Innocent, thank you.
Others will not get it.
Voltage is going to be the peak current, which is 2.83 times 5. And the answer is what now?
14.15.
14.15 volts. Because you can solve it differently. You can still say peak is root 2 times VRM. So you get the same answer. You follow this way. You get same answer. So the rest of what I will explain now, I will do an overview and end the video. Right?
7 minutes.
For it to be 2 hours. Okay, so let me summarize. So just screenshot this. So we're done with this. Now the next thing you want to know is that circuits, AC circuits, you can have different arrangements for an AC circuit. You can have purely resistive circuits. What do you need to know about a purely resistive circuit? For a purely resistive circuit, is a circuit actually that contains only a resistor. That is a purely resistive circuit. Now, for a purely resistive circuit, current and voltage are in phase. Take note of it. Current and voltage are in phase, which simply means that the phase angle between current and voltage is what? 0 degree. So you should know that. For a purely resistive circuit, the voltage across the resistor is I times the resistance. So you should know this. You should know that the phase angle for a purely resistive circuit is 0. Current and voltage are in phase. So it means that the phasor diagram is going to be like this. This voltage, this current. Both of them will be going in the same way. Or you can still do it this way, like this. This voltage, this current. This or this would represent the phasor diagram. So that is all for purely resistive circuit. Next is a purely inductive circuit. A purely inductive circuit contains only an inductor. Now, for a purely inductive circuit, voltage leads current. Voltage leads current, or you can say current lags voltage. Voltage leads current by a phase angle of 90 degrees or pi over 2. So that is for a purely inductive circuit. So for a purely inductive circuit, voltage leads current by a phase angle of 90 degrees. And the phasor diagram is like this. This is current, this is voltage, right? And then this is our direction of motion. So this is the phasor diagram for a purely inductive circuit. You don't want to draw it like this. You can draw it like this. You can draw it like this. This is still correct. Correct for a pure inductive circuit. Now there's something called inductive reactance. Inductive reactance denoted with XL. Inductive reactance in a common way is just the resistance of an inductor. That is inductive reactance, and it is measured in ohms. It's measured in ohms, and the formula is 2 pi FL. That is inductive reactance. So quickly, we are done with this. Then purely capacitive circuit. What is a purely capacitive circuit? A purely capacitive circuit is a circuit that contains only a capacitor. A circuit that contains only a capacitor. And for a purely capacitive circuit, the current leads voltage by a phase angle of 90 degrees. Current leads voltage by a phase angle of 90 degree. And what is the phasor or vector diagram? The vector diagram is going to be like this. Current is leading voltage. So if I draw this and this is my current, then this is going to be my voltage. For a purely capacitive circuit, you don't want to draw this way, you can draw this way. Put your voltage here, then you have your current. This still, any of these two is correct. Now for a purely capacitive circuit, there's something called XC. XC is actually the resistance of the capacitor. XC is known as the resistance of a capacitor, and XC is actually called the capacitive reactance. It is still measured in ohms because it is resistance. So it means that XC is going to be 1 over omega C, or you can just say 1 over 2 pi FC. So any of this can go for this. So you should take note of this for purely this. Then the voltage of the capacitor VC is going to be I times XC. The same way, voltage for an inductor is going to be I times what? XL. So these are things you should know. I have a short mnemonic for remembering this, which is Li, the ice man. This is the major thing here. E stands for EMF or voltage. Li, the ice man. So for this, E is voltage, L is inductance, I is current. Current, capacitance, voltage. So for the first one, you see that voltage comes before current. So you can say for a purely inductive circuit, voltage leads current, right? For a purely capacitive circuit, current leads voltage. So you can use that to remember this, right? Then you have what you know as RLC series circuit. RLC series circuit. RLC series circuit is a circuit that contains resistor, inductor, capacitor in series. That is RLC circuit. So when you have a circuit that contains these three things, it means that the resistance of that circuit is going to be a contribution from R, L, and C. So the resistance of an RLC circuit is known as impedance. The resistance of an RLC circuit or RL or RC circuit is known as impedance, and that impedance Z is given as this square root of R squared plus XL minus XC all squared. So you should take note of the formula for impedance. So I think these are basic things. And finally, one more formula you should know is formula for resonance frequency, which is 1 over 2 pi root LC. All these are formulas you should know, which summarizes AC. So I would suggest, so that we can stop this video at this point. Okay, then power factor, thank you. Power factor is the symbol cos phi. Power factor is PF, and the formula for power factor is cos phi, which is actually R over Z. So with these formulas, we have summarized this. So what you will do for those that will be writing exams tomorrow, go back to my YouTube channel, check, you will see all the teachings under AC. You can gradually look at it. You still have time before tomorrow. So I want to give a shout out to those that stayed till this point in time.
Top fans.
So,
Top fans.
top fans, thank you. Let me know them.
Innocent.
Congratulations.
Chukwuemeka,
Congratulations. Your A's are assured.
Chike
Chisom.
Ozi
Nuru. Okay.
Okuma, King Justice, Charles Igor, Nnadi Lotanna,
Okay, Daniel.
Nnadi
Lotanna, thank you. Pascal. Nkemjika.
Precious Ugu,
Chidimma. Obinna. Chinonso. Henry.
Roots, Miracle,
Ikechukwu,
Benjamin,
Chima,
Collins
came late. Uche, Elizabeth, Winifred.
Yeah.
Congratulations to all of you. Thanks for joining this live, and up till this point, I wish you guys good success in your exam that is coming up. Do well to like my video, comment, share this live. Immediately after it, I will post it, I will upload it and make it public. Then share with your friends that missed it. Tell them I'll be organizing another live session against the next week. This time around, I'll be going into waves, optics, and thermal physics. I'll be organizing a live session for wave and optics between now and Sunday. You'll be notified on when that class will hold. Thanks for participating in this video, Prime Concept. Let's end there, have you? Okay.